Alright, hello everyone. So, this comprehension is a doubt of one of the students. This is a question from rotation mechanics. So, very important, highly conceptual, quite complicated, and having multiple concepts associated. So, you all can pause the video and see there will be a lengthy discussion here because I will be solving all the four parts in detail. So here we have a rod which was initially almost like vertical-ish. It is hinged at one of its ends and free to move in a vertical plane. So let me tell you what is the initial situation. So initial situation is that the rod is almost vertical, like its angle with the horizontal is close to like 90 degree. So this angle is like around 89.99 degrees, and it is in contact with a box or a cube kind of thing. And because it is in contact with the cube, let me just draw the rod a little bit in such a way that it looks to be in contact with the cube. Okay, so this is how the rod is initially. As I was saying, this angle of the rod is almost like 89.99 degree. And so if it is released from rest, what will happen is that because of the mg, there will be a clockwise torque about the hinge, and so this rod will start to rotate clockwise. As the rod will rotate clockwise, the box that you can see, which is by the way placed in a frictionless surface, all surfaces are smooth, okay. So this box will be going towards right. As the box goes towards right, the rod will fall more and more, and a time will come when the rod has fallen and the box has gone away, and the contact between them is lost. In fact, we have to find out when does the contact breaks between the rod and the box or block, whatever you call it. In fact, it is already given that it happens when angle with the horizontal becomes 30 degrees. So theta is equal to 30 degree. At that point it happens, or when the rod has rotated clockwise by 60 degrees from its vertical position. That is the moment at which the contact breaks. And for that to happen, I mean the contact to break at that point, what should be the ratio of the mass of the rod and the block? Okay, so the thing is, here also there is a smooth surface, no friction at all. And if you take the rod and the block as a system, so if you draw the free body diagram, we know that net work done by normal force action reaction pair between two surfaces is 0. So there is a work done by normal force by block on the rod, by rod on the block. These two guys are applying normal force on each other, N, or let's call it N1, N1. So the net work done by N1 and N1 action reaction both is 0. N1 on the block from the rod, which is this N1, does positive work on the block and gives us a forward kinetic energy, and this N1 on the rod will do negative work on the rod. Now as far as the free body diagram of the block is considered, there is a mg force on the block itself, and then there is a normal force from the ground, and then you can say that this rod will also experience some gravity force, and on top of that there is a hinge force on the hinge reaction. Let's call it nx and y. So the hinge forces don't do any work, the normal force from the ground not doing any work because it's vertical force, whereas displacement of the block is horizontal. Same way this mg force is also not doing work because the force is vertical on the block, whereas the displacement of the block is horizontal. So not doing any work, net work done 0, and hinge forces anyway don't do any work. So only force which is doing work is this mg, which is a conservative force. Because only conservative force is doing work, the total mechanical energy is constant, and so we can say that the decrease in potential energy is getting converted into the increase in kinetic energy of this system. So what is our system? The system is equal to block plus rod, and let us write the mechanical energy conservation. Okay, so after some time, let's say the block has already fallen, so its potential energy has reduced. In fact, that reduction in potential energy is utilized to convert or to gain into kinetic energy. So when this rod would have rotated by angle theta or something. Do you want to take this as theta, or you want to take the the angle with the horizontal as theta? It's your choice. Let us take the angle with the horizontal as theta. So the initial position of center mass of the rod is L by 2. After some time, after it has fallen clockwise by an angle of 90 minus theta, then its height of the center mass is L by 2 sine theta. So what is the decrease in potential energy of rod? That is equal to mg L by 2 minus L by 2 sine theta. For the purpose of calculation of decrease in potential energy, we do consider the decrease in height of center of mass. So there's decrease in potential energy of the system is equal to increase in kinetic energy of the system. The system consists of rod and the block. We can't simply conserve the mechanical energy of the rod alone, because the rod is getting this force N1, and because of if you take only rod as a system, then for only rod the problem is that the block will apply a normal force, and this normal force from the block is doing negative work and extracting some energy. In fact, what these two guys are doing, this rod and the block, via the help of normal force that they apply on each other, they are transferring energy from one to the other, from rod to the block. And because of that, what is happening is the energy transfer is happening from the rod to the block, and so the overall energy is constant, but not constant of a single rod alone. So whatever is the potential energy reduction of the system is equal to increase in kinetic energy of the system. As far as the rod is considered, when it is rotating purely about a fixed axis, its kinetic energy can be written as half I about the axis of rotation into omega square, and for the block, which is translating simply, half mv square. Now there is a relation between the velocity and the omega. What is that relation also? Let me tell you. Okay, so this is the energy conservation done. What are the unknowns here? The unknowns here are omega and v. However, omega and v are related to each other, because till the time this two are gaining energy from each other or transferring energy between each other, they are in contact with each other and they are applying normal force on each other. So when that is happening, we can say that let's say this is the corner point of the rod which is in contact with the block. So when the rod is rotating, this point A is moving in a circle with center as the hinge. So A is moving in a circle like this, okay, and the radius of the circle is L. So for its circular motion, the velocity of A is tangential, and if the angular velocity of the rod is omega, then A's velocity is omega L. Now if you talk about this B point, which is a point on the block, this B point is going towards right with a velocity v. The thing is, always this A and any point in this line are in contact with each other, which means their forward displacements are same, isn't it? Which means when this rod, this block will go like this, the A will come here. So A has come from A to A dash. So how much is the horizontal displacement of A? Horizontal displacement of A is same as horizontal displacement of the block, which means A's horizontal velocity is same as block horizontal velocity. Apart from that, A can be going down also. See, you may remember the wedge constraints, like component of velocity along the line joining them, perpendicular to the surface in contact, that component of velocity is same. So wedge constraint also, you can say this is a kind of wedge constraint. So basically, if you take that this angle is theta, then this angle is also theta. This is 90 degree, this is 90 minus theta. So what is the horizontal component of omega L? Horizontal component of omega L is omega L cos of 90 minus theta. So omega L cos of 90 minus theta, basically omega L sin theta, that should be equal to the velocity. So this is what we get. So we got V is equal to omega L sin theta. Okay, now from here what we will get is, we will get a velocity v or omega as a function of angle theta. So this is point number 1. Now when will the contact be broken? Let's try to understand this. So for that, let's try to understand the acceleration of point A. So if this is a point A, this point A is moving in a circle with center as hinge, and for its circular motion about hinge, in circular motion there are two components of accelerations. So one component of acceleration is omega square into radius, which is the centripetal acceleration, which is towards the center, and other acceleration is the tangential acceleration, which is r alpha. Okay, so we have to calculate the total acceleration of A. So for that we need to calculate the alpha also. So let us calculate the alpha with tau is equal to I alpha. However, before doing that, let us try to understand another logic here. Let us say that we resolve the A's acceleration into horizontal and vertical components. So this angle theta, so the alternate interior theta, so this is 90 minus theta. Okay, 90 minus theta. So what is the horizontal acceleration of A? Acceleration of A horizontal, if we talk about only the horizontal acceleration, it is r alpha. R alpha has got a horizontal component cos of 90 minus theta, which is sin theta, and then it has also this backward acceleration, which is this angle is theta, so omega square L cos theta. Okay, omega square L cos theta. Now this horizontal acceleration of A initially will be towards right. The reason is because initially the omega is very small. Okay, now as the rod keeps rotating, initially it was vertical, omega was almost 0. As it keeps rotating, it keeps gaining omega. So as it keeps gaining omega, this omega keeps increasing. So what happens is, because of this, the second term, it starts dominating later on. Initially the first term will be dominating, and later on the second term is dominating. So initially it has got a towards right acceleration, this A, and it keeps gaining towards right velocity because of the overall towards right. But as the rod keeps rotating, this omega becomes very high, and because its omega becomes very high, so the second term starts to dominate. In fact, when the rod has rotated completely like this, by that time it has already got a very high omega, and the overall acceleration towards right, the overall acceleration in horizontal direction is actually in the left direction. So you can say that this horizontal acceleration of A toward right is initially equal to r alpha sin theta minus omega square L cos theta. Because this r alpha sin theta is higher initially and this omega square r is lower initially, so the overall acceleration is positive in towards right direction, you can say. Later on what will happen is, this will be less and this will be more, so overall this entire thing will become negative, which means the acceleration which we have chosen to be towards right, actually it will become towards left. So acceleration is going to change after some time from right to left. Now let's say if there is a object and then there is another object in front of it. Let's say this is object A, this is object B. Now let's say if object A starts to increase its velocity, then obviously it must push B and increase B's velocity also in the same manner. Because if A has to increase its velocity towards right, it wants to move faster, it can't go inside B, so it needs to push B and make B also move along with it with higher velocity. So till the time A wants to increase the horizontal velocity, it needs to increase B's horizontal velocity also. For that it needs to keep pushing B, for that normal force will keep acting between them. But once A decides to reduce its velocity, apply brakes, B's velocity it can't reduce, B will keep going with the same velocity with which it was going, and contact will be broken. So if A is increasing its velocity, it will increase B's velocity and contact will be maintained. But when A's acceleration changes from positive towards right to negative towards left, or retardation or decreasing velocity, that is when the contact breaks. So contact will break when the acceleration of A is changing from positive, which is towards right, to negative, which is towards left. While changing from positive to negative, the horizontal acceleration of A will become 0. So the funda is that when A's acceleration is changing from positive to negative and thus passing through 0 value, that is when contact between A and B is gone or broken. So exactly that is what happens. Here we have A and B. So till the time A is horizontal, velocity keeps increasing, the contact is broken. But as I said, the horizontal acceleration of A changes from towards right to towards left after some time, and because of which at a single moment of time, when its when its horizontal acceleration is 0, that is the moment at which the contact is broken. So here we have to understand, when does the contact break? When does the contact break? When this entire thing becomes 0 value, because it is turning from positive to negative. So at the contact breaking, we will say that this is equal to this. So let's talk about the contact breaking. At contact breaking, we can say that omega square L, what was that? Omega square L cos theta and R alpha sin theta. So this is the contact breaking condition. Let's call it as equation 2. Now contact has just broken at this particular angle theta, which is given to be 30 degree. At this contact breaking condition, what is alpha? So let us see. At the contact breaking condition, we have to calculate the alpha. For that, tau is equal to I alpha. Now contact is breaking at this moment, so normal force on the rod is 0 from the block, which means apart from that normal force which is 0, there is a mg force at this angle theta, and apart from that there are hinge reactions which don't provide any torque at all about the hinge. So torque about the hinge will be mg L by 2 cos theta, and that will be equal to ml square by 3 into alpha. So what is the contact breaking alpha? The angular acceleration at the time of contact breaking, which means at the time when normal force becomes 0 and only mg is providing the torque, at that moment what is the alpha? Alpha is 3g by 2l cos theta. So this is the alpha at that moment, precise moment when contact is broken. And what is the omega at that precise moment? So for that we have to use the energy conservation. This is becoming very lengthy. So this is the energy conservation equation, in which I will put V as omega L sin theta. V is equal to omega L sin theta. The good thing is that already this theta is given at which contact breaking happens. So we can put the values. So omega square, so in this equation we put the values of alpha and theta. So omega square L into cos theta. Cos theta is cos of 30 degree is equal to R. R is the radius for the circular motion of A, which is L only. So this R is L. Then alpha is 3g by 2l cos theta. Cos theta is again root 3 by 2 into sin theta. Sin theta is half. So at the contact breaking situation, L, do we have to cancel out this L? Maybe not. Root 3 by 2 we will cancel it. So omega square L is equal to 3g by 4. Now omega square L is 3g by 4 at the moment of contact breaking, which is at theta equal to 30 degree. So mg into L by 2, 1 minus, so sine of at contact breaking sin theta is 30 degree, I mean sine of 30 degree, half ml square by 3. What is omega square? Omega square is 3g by 4l plus half m into v square. Now v square will be omega square into L square into sin square theta. Omega square L square sin square theta. So let us rewrite this entire thing once again, but this time we will substitute the omega square value in the last term also. So how much is that omega square? So this omega square is 3g by 4l. So let me just little bit drag this, remove omega square and put 3g by 4l. And also sin square theta. What is sin square theta? At contact breaking, sin square theta is 1 by 4. So finally we got something out the other, I suppose. We'll cancel out g from all the sides and l also from all the sides. And what do we get? We get m by 4 is equal to m by 8 plus this is 3m by 16. It is coming 4 into 4, sorry, 32. So we get m by 8 is equal to 3m by 32, which means m by m is equal to 3 by 4, which means for contact breaking to be happening at 30 degree, small m by capital M is 3 by 4. So this is the first part, the value of ratio 3 by 4, m by m is 4 by 3, capital M by small m. Velocity of the block when the rod loses contact with the block, which means omega only we are talking about. Velocity of the block, okay, block velocity. So block velocity is omega L sin theta. So V of the block is equal to omega L sin theta at the time of contact breaking. Omega is, how much is omega? I forgot. Omega square. So omega square is 3g by 4l. So omega is root over 3g by 4l. So let me put the value 3g by 4l as omega. 3g by 4l with the root is omega into the length into sine of 30 degree, right? Half. So what do we get here? Root over 3g L by 16. So root over 3g L by 16 is the block's velocity. 3g L by 16 it is, oh, no option is there. Okay, inside the root we have 16 now. Yeah, so root over 3g L by 16 means root over 3g L by 4. So 4 will be outside the root, so we're getting A option. Acceleration of center mass of the rod when it loses contact with the block. Oh, that's horrible. Acceleration of center mass of the rod. So center mass is moving in a circle, so it will have two accelerations. So one will be the centripetal, one will be the tangential. But now we are talking about the center mass. So center mass are tangential acceleration and centripetal. So centripetal acceleration is omega square L by 2, because the radius for the circular motion of center mass is L by 2. Center mass is at the midpoint, and with respect to the hinge it is moving in a circle of radius L by 2. As far as tangential acceleration is considered, it is alpha L by 2. So what is the total acceleration? Like you have to, so basically you already know omega square as 3g by 4l. So if you put this omega square as 3g by 4l and multiply it by L by 2, you get 3g by 8. Okay, so the centripetal acceleration of center mass is 3g by 8, and then comes the tangential acceleration. Tangential acceleration is alpha L by 2. So 3g by 8 and alpha L by 2. How much is alpha? So let us calculate alpha also here. We need alpha at contact breaking. At contact breaking, 3g by 2l into cos of 30 degrees root 3 by 2. So we get 3 root 3 by 4g by l. But we know, but this is alpha. We need alpha into L by 2. So I'm going to multiply it by L by 2 here. And we get 3 root 3g by 8. So one acceleration is 3g by 8. Other acceleration is 3 root 3g by 8. So what is the total acceleration of center mass of the rod? Root over its centripetal acceleration square plus tangential acceleration square. As far as the centripetal acceleration is considered, I think we got 3g by 8. And tangential acceleration 3 root 3g by 8. So we will take 3g by 8 as common, root over 1 plus root 3 square. So basically we get 3g by 4. Oh, that's simple. How simple? 3g by 4. So the acceleration of center mass is simply 3g by 4. Then comes the hinge reaction at O on the rod when it loses contact. So the good thing is we already know the acceleration of center mass. So the last part will be like this. We have to draw the free body diagram. Good thing is that the normal force from the block is 0 at the contact breaking, and so the forces will be only the hinge force Ny and Nx, and the mg force. So what is the net force? Net force is Ny in j cap, Nx in I cap, and mg in minus j cap. So this is the net force on the rod, and net force on the rod is equal to mass into acceleration of center mass of the rod. As far as the center mass of the rod is considered, its acceleration is 3g by 8, and tangential acceleration is 3 root 3 g by 8. Now this angle is 30 degrees, so let us resolve this acceleration components which are centripetal and tangential, and we are going to resolve these two component of accelerations into their components along x and y. Okay, so this is 3 root 3 g by 8, which will have a component. So this angle is 60 degree. So what are the components do we get? The component that we get are like this. So this component is 3 root 3 g by 8 into cos 60, which is half. And what about the component of this 3g by 8? 3g by 8 will have a backward component of 3g by 8 into cos of 30 degree. Cos of 30 degree is root 3 by 2. So we get 3 root 3 g by 16. The good thing is that these two accelerations cancel out each other. So overall acceleration of center mass is 0 in horizontal direction. Then what is the vertically downward direction? For that we need the component of the tangential acceleration in the minus y direction. So 3 root 3 g by 8 has got a 3 root 3 g by 8 has got a sine 60 component, I suppose. Sine 60, huh? Yeah, so root 3 by 2. So we get 3 into 3, 9g by 16. And what about the component of 3g by 8? 3g by 8 also has a vertical component, which is 3g by 8 into sine of 30 degrees. Sine of 30 degrees is half. Again 3g by 16. So we are getting 3g by 16, and also we are getting 9g by 16. So total become 3g by 16 plus 9g by 16, 12g by 16. 12g by 16 means 3g by 4. So the net acceleration of center mass vertically is 3g by 4. I think we already calculated it now. So net force is equal to mass into acceleration of center mass. So this is the net force, and net force is equal to mass into acceleration of center mass. Now so equating the coefficients of g cap on both the sides, so ny minus mg is equal to minus mg into 3 by 4. So ny is equal to mg by 4, and comparing the horizontal, the I cap coefficients on both the sides, we get nx is equal to 0. So how much is the hinge reaction? Hinge reaction is only mg by 4 in vertically upward direction at the moment of contact breaking. Only mg by 4, my dear. So this is B option. Thank you so much for your patience. See, these kind of questions you should not be afraid of, but you should be actually practicing. This will really help you to solidify your understandings in rotation. So don't get scared away, don't run away, and tackle these questions head on.